So in this question, we're asked to use Simpson's rule with 6 intervals to estimate the integral between 1 and 4 of the square root of 1 plus x cubed with respect to x. This question is 5 marks. So the first thing we need to do is remember what Simpson's rule is. Well, like the trapezium rule, it is an approximation that uses quadratic polynomials in order to estimate the area under a curve. You're not given the Simpson's rule in your data book, so you need to remember what it is. The formal formula of the Simpson's rule states that the area under a curve is approximately equal to h over 3 times by y0 plus 4, y1 plus y3 plus y5, etc., plus 2 plus y4 plus y6 plus etc., plus yn, where n is an even number of strips or intervals, and where h is equal to b minus a over n, which is the width of each strip. If you think you'll struggle to remember this in the exam, you can think of it as such. The area under the graph is approximately equal to the step length over 3 multiplied by the start plus 4 times the sum of odds plus 2 times the sum of evens plus the end. So the first step to estimating this integral is calculating the step length, h. Well, h is equal to b minus a all over n. Well, we know b and a because b is just 4 and a is just 1. So h is equal to 4 minus 1 all over. Well, now we need to find the value of n. Well, n is the even number of strips or intervals. And our question tells us that we need to use 6 intervals, and thus the value of n that we need to use is 6. So it's 4 minus 1 over 6, and this is just equal to 0.5. So that's our step length. Wait, so now we need to find the y values corresponding to the correct x values. Well, in order to do this, let's set up a table. We have x over here and y over here. And we want to find out the values of y which correspond to each section of our interval. Well, we know that our step length is 0.5, so that means that if our graph looks something like this, and this is 1, and this is 4, each step will be 0.5 in width, so we will have x0 as 1, x2 will be 1.5, x3 will be 2, x4 will be 2.5, and so on until you get 4. So let's write this down. x0 will be 1, x1 will be 1.5. Remember, we're adding 0.5 each time because this is our step length. x2 will be 2, and so on, remembering to add 0.5 each time. We stop when we get to 4 because that's our final ordinate. Now we need to find the corresponding y values when x is equal to 1, 1.5, 2, and etc. So let's write out y0, y1, y2, y3, y4, y5, and y6. Well, y0 will be the value of our function, root 1 plus x cubed, when x is equal to 1. So once again, our function is equal to root 1 plus x cubed. So our value of y0 will be root of 1 plus 1, which will just be root 2. So y0 will be root 2. y1 will be root of 1 plus 1.5 all cubed, which will be root 4.375 to 3 decimal places. Let me spread out this a bit more so I have more space to write. So we have root 2 for y0, and for y1 we have root 4.375. Remember, you get the values of y by substituting our values of x into our function and putting it into our calculator. I'm leaving it to 3 decimal places over here because we want as many significant figures as possible in order to get the most accurate approximation at the end. For y2, you get root of 1 plus 2 cubed, which will just be root of 9, so that's 3. And for y3, you do root 1 plus 2.5 all cubed, which is 16.625 all square rooted to 3 decimal places. For y4, you get root of 28. For y5, you get root 43.875. And for y4, you get root 65. Great, so now we know our corresponding values of y for each ordinate of our intervals. Now let's plug in our values of y into our formula for Simpson's rule. So we have h, which is 0.5 over 3, multiplied by, well, y0 will be root 2, plus 4 times the odd ordinates. So it would be root 4.375 plus root 16.625 plus root 43.875 plus 2 times the sum of the even y. So we will have 3 plus root 28. Now we don't add y6 over here because y6 is our last ordinate or our last value of y. So our yn in this case will be y6, which will just be root 65. Now if you put the thing inside our brackets into a calculator, you get approximately 77.23. So our integral will now be approximately equal to 0.5 over 3 multiplied by 77.23 approximately. And this is just equal to 12.9 to 3 significant figures. And thus, that is our approximation of the area under the graph using Simpson's rule, with 6 intervals. Now that we've answered our question, let's find out where the marks are. You get 1 mark for finding out the step length. You get another mark for forming a table and finding out the corresponding values of x and y, for x0, x1, etc., and y0, y1, etc. You get another mark for putting it into our formula and finding out the value of 77.23, which is inside the brackets over here. You get another mark for putting it into our formula as a whole, so by doing 0.5 over 3 multiplied by 77.23. And you get your final accuracy mark for arriving at the correct conclusion, which is 12.9. In this question, we're given that k is a constant and that y is equal to x cubed times by e to the power of kx. We need to use Leibnitz's theorem to show that the nth derivative of y is k to the power of n minus 3 times by e to the power of kx multiplied by k cubed times by x cubed plus 3nk squared times by x squared plus 3n times n minus 1 times k times x plus n times n minus 1 times n minus 2. Well, Leibniz's theorem is very similar to the product rule in the sense that it allows us to use binomial coefficients in order to find out the nth derivative of the product uv. So in formal terms, the nth derivative of uv is equal to the sum between r is equal to 0 to n of n choose r times by the rth derivative of u times by the n minus rth derivative of v. Now it must be stressed here that this notation that looks like uv to the power of n isn't to the power of n. It's a notation that allows us to express functions, or the derivative of functions, more concisely. For example, if you have a function f and you want to find out the nth derivative of f, you can rewrite it as f of n of x is equal to the nth derivative of x. Similarly, f of 0 of x will just be f of x, because the 0th derivative of f of x will just be f of x. Great, so now that we have this formal definition, how can we use it to answer our question? Well, the first step to doing this is to find out what exactly u and v are. Well, if we look at our question, we have x cubed multiplied by e to the power of kx as our function uv of x. So we can write that uv of x is equal to x cubed multiplied by e to the power of kx. Now let's try u is equal to x cubed and v is equal to e to the power of kx. Now in order to use Leibniz's theorem, we need to be able to find the derivatives of u and the derivatives of v. Let's assume that u of x is equal to x cubed and v of x is equal to e to the power of kx. We need to find the derivatives of u and the derivatives of v. For example, let's write out the first term of Leibniz's theorem using this formula, in which case when r is equal to 0. So when r is equal to 0, the first term will be n choose 0 multiplied by the 0th derivative of u multiplied by the n minus rth derivative, well, r is equal to 0, so it would just be n minus 0, which would just be n of v, and this would be our first term. Similarly, if we were to increase r by 1, we will have n choose 1 multiplied by the first derivative of u multiplied by the n minus 1 derivative of v. And you can see the pattern as represented by the formula over here in the more expanded form, that each time you're going to increase the value of r by 1, and thus you'll need to differentiate to u n times. So let's differentiate to u and v respectively. Well, the 0th derivative of u will just be x cubed, and we need the nth derivative of v in order to find our first term. Well, it's not immediately obvious about how we can find the nth derivative of v. However, you can note that v is actually an exponential function. So v of x is equal to e to the power of kx. So let's find the first derivative of x. And in order to do this, you're going to bring the k, or the constant, down to multiply with our original function v of x. So we have k e to the power of kx. Let's differentiate this again to form the second derivative of v, which will be k squared e to the kx, as once again you're bringing down the constant from our power, multiplying it by our original function, giving you x squared e to the power of kx. And you can notice that every single time you differentiate, you're actually just going to be multiplying our original function that we had with another k. So thus, v to the power of nx will just be k to the power of n e to the power of kx, because each time you're just multiplying the previous function by k, so you're effectively adding 1 to the power that you already had in your original function. Well, we can use this information in order to find the nth derivative of v of x. So we have the nth derivative of v is equal to kn e to the kx. Now let's continue finding these terms by differentiating both the left-hand side and the right-hand side. So the first derivative of u will be equal to the derivative of our initial function, which is just 3x squared, and our n minus 1 derivative of v will be k to the power of n minus 1 e to the kx, and our second derivative will be 6x, and similarly our n minus 2 derivative of v will be k to the power of n minus 2 e to the kx. Our third derivative for u will be 6. Our n minus third derivative of v will be k to the power of n minus 3 e to the kx. And here's where it gets interesting. Our fourth derivative of u will be 0. And so will our fifth derivative, and so will our sixth derivative, and so will etc. Because if you differentiate 0, you're just going to get 0 again. And thus, once you reach the fourth derivative of u, every single differentiated function after that will just be 0. Now, if we look at our formula for Leibnitz's theorem over here once again, each term of our differentiated function is calculated by multiplying the rth derivative of u times by the n minus r derivative of v. Well, what happens if the rth derivative of u is 0? Well, anything multiplied by 0 will just be 0. So thus, any further differentiated function of v that has r is greater than 3 will just cancel, because you'll have 0 multiplied by the differentiated function of v, and that would just be 0. Let's illustrate this using the specific example of r is equal to 4. Well, when r is equal to 4, our term will be n choose 4 multiplied by the fourth derivative of u multiplied by the n minus fourth derivative of v. Well, the n minus fourth derivative of v will be k to the power of n minus 4 e to the kx. But the fourth derivative of u will just be 0, and thus this entire term will be 0. We can continue this for any value of r greater than 4, because any value of r greater than 4 will result in the rth derivative of u, and thus we really only need to care about these first 4 terms. So from when r is equal to 0 to r is equal to 3. Similarly, we only need to care about the last 4 terms of our derivatives of v, because these are the terms that will be multiplied with our first 4 terms of the derivatives of u. So let's apply Leibniz's theorem to our differentiated functions of u and v that we found over here. Well, because our function of uv will just be y, then our nth derivative of y will be equal to n choose 0 because we want to find when r is equal to 0. The rth derivative of u when r is equal to 0 will be x cubed. So n choose 0 multiplied by x cubed multiplied by the nth minus r derivative of v, which would just be the nth derivative of v, which would be kn times by e to the power of kx, plus n choose 1 multiplied by the first derivative of u, which is 3x squared, multiplied by k to the power of n minus 1 e to the kx. Notice in my working out, I've actually lined up the function together so that they would be multiplied by the function directly opposite it. So my second derivative of u will be multiplied by my n minus second derivative of v. So we have n choose 2 multiplied by 6x multiplied by k to the power of n minus 2 e to the power of kx. And finally, our last term will be n choose 3 multiplied by 6 multiplied by k to the power of n minus 2 e to the power of kx. This should all be on one line, but I ran out of space, so I left the last term on the second line. Now, once again, any single term after this will just be zeros, so we don't need to include it in our expansion. Let's expand out this expression by expanding out the choosers. Now, in order to expand out the choosers, you need to remember that n choose r is equal to n factorial all over r factorial times by n minus r factorial. You're given this in your formula book though, so if you forget it in the exam, you can look in your formula book. The exceptions to this being n choose 0 is equal to 1 and n choose n is equal to 1. And thus, the nth derivative of y is equal to, well, n choose 0 will just be 1, so it will be x cubed multiplied by k to the power of n e to the kx plus n choose 1, which will be n factorial all over 1 factorial multiplied by n minus 1 factorial multiplied by 3x squared multiplied by k to the power of n minus 1 e to the power of kx plus n choose 2, which will be n factorial all over 2 factorial multiplied by n minus 2 factorial times by 6x multiplied by k to the power of n minus 2 e to the power of kx plus n choose 3, which will be n factorial over 3 factorial multiplied by n minus 3 factorial multiplied by 6 multiplied by k to the power of n minus 2 e to the power of kx. And once again, these are all the terms that we have because the rest of the terms will be 0. Now let's simplify this a bit more. So we have the nth derivative of y is equal to x cubed times by kn e to the power of kx plus, well, n factorial all over 1 factorial times by n minus 1 factorial will be n factorial over n minus 1 factorial. And if you recall what factorials are, n factorial is equal to n multiplied by n minus 1 multiplied by n minus 2 all the way to 1. Similarly, n minus 1 factorial will be equal to n minus 1 multiplied by n minus 2 multiplied by n minus 3 all the way to 1. And thus, n factorial divided by n minus 1 factorial will be just n, because all of the terms after the n minus 1 and including the n minus 1 will cancel if you do n factorial divided by n minus 1 factorial. It will be n multiplied by 3x squared times by k to the power of n minus 1 multiplied by e to the power of kx plus, well, we can apply the same logic we used in order to find n factorial over n minus 1 factorial. In order to solve n factorial over n minus 2 factorial, as n factorial divided by n minus 2 factorial will cancel all of the terms except for n and n minus 1. So it will be n times by n minus 1 divided by 2 factorial, which is just 2, multiplied by 6x times by k to the power of n minus 2 e to the power of kx plus, once again, n factorial over n minus 3 factorial will be n multiplied by n minus 1 multiplied by n minus 2 all over 3 factorial, which is just 6, multiplied by 6, multiplied by k to the power of n minus 3 e to the kx. I just realised over here this should be a 3 because r is equal to 3 in this case, not 2. You can simplify this even further by taking out a factor of k to the power of n minus 3 times by e to the power of k of x out of all of these terms. So the nth derivative of y is equal to k to the power of n minus 3 times by e to the power of kx multiplied by x cubed times by, well, k to the power of n divided by k to the power of n minus 3 will be k to the power of 3 plus n multiplied by 3x squared multiplied by k squared, because k to the power of n minus 1 divided by k to the power of n minus 3 will be k squared, plus, well, n minus 1 times by n multiplied by 6x squared all over 2 will just be n times n minus 1, 3x, times by, well, k to the power of n minus 2 divided by k to the power of n minus 3 will just be k, plus our final term. Well, we have a 1 over 6 over here and a 6 over here, so this will cancel to just give you 1. I will take out to k to the power of n minus 3 times by an e to the power of kx out of this bracket, so it will just leave us with n times n minus 1 times n minus 2. And if we scroll back up to our question, this is awfully similar to what we have over here. In fact, it's exactly the same, except that some of the products are rearranged in the wrong order. So let's fix that really quickly. And this is exactly the same as what we have on top over here. And thus we've solved our question. So now that we've solved our question, let's find out where the marks are. You get a method mark by identifying that u is equal to x cubed and thus finding the derivatives of that up to the third derivative, because every single term after that will just be 0. You get another mark by identifying that v should be e to the power of kx and thus finding the nth derivative, the n minus 1 derivative, and so on of v. You get another method mark for writing down our actual Leibniz's rule, stating that the remaining terms are equal to 0, so you won't have the remaining terms. And you get your final accuracy mark for arriving at the correct show that, giving you a total of 4 marks overall. In this question, we're given that a vibrating spring fixed at one end has an external force acting on it such that the center of the spring moves in a straight line. At time t seconds, where t is greater than or equal to 0, the displacement of the center C of the spring from a fixed point O is x micrometers. In other words, at time t, the spring has a displacement of x micrometers. The displacement of C from O is modeled by the differential equation t squared multiplied by the second derivative of x with respect to t minus 2t multiplied by the first derivative of x with respect to t plus 2 plus t squared multiplied by x is equal to 4. For part A, we need to show that the transformation x is equal to tv transforms the equation I, which is this equation over here, into the equation the second derivative of v with respect to t plus v is equal to t. Well, because we're given a transformation that x is equal to tv, we know that this question wants us to tackle reducible differential equations, where we use our substitution in order to reduce this differential equation I into something that we can more easily solve, because t is a variable, and thus we can't use our conventional methods in order to solve this differential equation. Now, because I wants us to find the derivative of v instead of the derivative of x, we need to substitute the second derivative of x and the first derivative of x with functions in terms of v and t, because there are no x's in our equation I. So how do we do that? Well, we're given over here that x is equal to tv, and thus we can actually find the first and the second derivatives of x with respect to t by differentiating the entire equation with respect to t twice. So for example, we are given that x is equal to tv. So dx by dt will be equal to, well, we have differentiated the left-hand side, so we need to differentiate the right-hand side. How do we differentiate the right-hand side with respect to t? Well, tv is a product of t and an unknown variable v. And in order to differentiate the product of these variables with respect to t, we need to use the product rule, where the derivative of uv is equal to the derivative of u multiplied by v plus the derivative of v multiplied by u. Well, u in this case will be t, so the derivative of t will just be 1 with respect to t. So it will be 1 multiplied by v plus, well, we can let v in our product rule equation be v in our original equation. So the derivative of v with respect to t will be dv by dt multiplied by u, well, u is t, so it will be dv by dt multiplied by t. And thus we have found dx by dt. Now we can simplify this a bit to give you dx by dt is equal to v plus t multiplied by dv by dt. Now we have dx by dt, but what we want to find as well is the second derivative of x with respect to t. So in order to find the second derivative of x with respect to t, we need to differentiate dx by dt once again. So the second derivative of x with respect to t, well, if we differentiate v with respect to t, we get dv by dt once again. Now this over here will require us to use the product rule once more. So the derivative of t with respect to t will be 1, so it will be plus dv by dt, and the derivative of dv by dt will be the second derivative of v with respect to t. So it will be plus t multiplied by the second derivative of v with respect to t. We can simplify this once again to give you 2 multiplied by dv by dt plus t multiplied by the second derivative of v is equal to our second derivative of x with respect to t. Great, so now that we have dx by dt and the second derivative of x with respect to t, we can substitute this back into our equation I in order to find out an equation in terms of only v and t variables. So let's substitute our dx by dt, our second derivative of x with respect to t, and our x, which we can recall is equal to tv, into here. So we get t squared multiplied by, well, the second derivative of x with respect to t will be 2 dv by dt plus t multiplied by second derivative of v with respect to t. So it will be 2 dv by dt plus t multiplied by the second derivative of v minus 2t multiplied by dx by dt. Well, we found that dx by dt is equal to v plus t multiplied by dv by dt. So it will be times by v plus t multiplied by dv by dt plus 2 plus t squared multiplied by x. Well, x is equal to tv, so we x is equal to t to the power 4. Well, t squared multiplied by 2 dv by dt is equal to 2t squared multiplied by dv by dt plus t squared multiplied by t multiplied by the second derivative of v with respect to t will be t cubed multiplied by the second derivative of v with respect to t minus 2t v, because you're going to multiply 2t with v, and then you have to multiply 2t by t multiplied by dv by dt, give you minus 2t squared multiplied by dv by dt plus dv multiplied by 2 plus t squared is equal to t to the power 4. Now you have a 2t squared multiplied by dv by dt and a minus 2t squared multiplied by dv by dt, so we can cancel these out. T cubed multiplied by the second derivative of v minus 2tv plus tv multiplied by 2 plus t squared is equal to t to the power 4. Now you can also notice that there is a common factor of tv for our 2tv and our tv multiplied by t plus t squared over here, and thus we can group these terms together to give you t to the power 3 multiplied by the second derivative of v with respect to t plus tv minus 2 plus the bracket over here, which is 2 plus t squared, is equal to t to the power 4. This can be simplified because minus 2 plus 2 is equal to 0 to give you just t to the power 3 multiplied by the second derivative of v plus t cubed multiplied by v is equal to t to the power 4. Now we can divide both sides by t cubed to give you the second derivative of v with respect to t plus v is equal to t. And if we look back at our question, we want to show that the transformation x is equal to tv transforms equation I into our equation, the second derivative of v plus v is equal to t, with no x variable in our differential equation. So thus we've shown our result. Great, so now that we've answered our question, let's find out where the marks are. You get 1 mark for using x is equal to tv to give you our first derivative over here, that dx by dt is equal to v plus t multiplied by dv by dt. So this is 1 mark. You get another mark for using this in order to find our second derivative over here. And we get an accuracy mark for doing these correctly. And we also get another mark for substituting in our values of dx by dt and the second derivative of x with respect to t into our original equation I. And finally, you get your final accuracy mark for arriving at the correct show that. In part B, we need to find the general equation for the displacement of c from O at time t seconds. Now, the first thing you should think about when analysing this question is that they asked for the displacement of c at time t seconds. Right now we have our variable v, but we want the variable of x in our equation, because x is the displacement in micrometers. So at some point we need to convert our differential equation such that the solution is in terms of x and t instead of v and t. So we should keep in mind that x is equal to tv, and thus v is equal to x all over t. Now we can solve this differential equation. The second derivative of v with respect to t plus v is equal to t, because we know how to solve second order differential equations. So in order to solve second order differential equations, we need to first find the auxiliary equation in order to find our complementary function, and then find our particular integral and add them together. So our first step is finding the auxiliary equation. So our auxiliary equation would be m squared plus 1 is equal to 0. And we need to solve this equation in order to find m. So in this case, m will be equal to plus or minus I. Well, if m is equal to plus or minus I, we know that our complementary function will then look something like this. E to the power of the real part, well, the real part is 0, so it will just be e to the power of 0, which is just 1. So it will just be 1 multiplied by a cos the coefficient of the imaginary part, which is just 1. So it will just be t plus b sine t. So thus we know our complementary function. Now we need to find our particular integral. Well, the way we do that is by noting that on the right hand side we have just a t. So we have a linear expression on the right hand side. And thus our particular integral will be something of the form Vp is equal to lambda t plus mu. Let's find the derivatives and the second derivative of this in order to substitute back into our original equation. So the derivative of this will just be equal to lambda, and the second derivative of this will be equal to 0, because the derivative of a constant is equal to 0. Let's substitute this back into our original equation. So we have 0, because we have the second derivative of v, so 0 plus v, which is just lambda t plus mu, is equal to t. Now we need to find our coefficients lambda and mu. Well, mu will be equal to 0 because there are no constants on the right hand side, and lambda will be equal to 1 because the coefficient of t on our right hand side is just 1. So lambda is equal to 1. Hence, we know that our particular integral will be just t. So v is equal to our complementary function plus our particular integral, which is just equal to a cos t plus b sine t plus t. Now once again, this is an equation for v, but we want an equation for x. Now because of our original substitution, we're given that v is equal to x over t, and thus we can substitute x over t for v in this equation over here to give you x over t is equal to a cos t plus b sine t plus t. And thus we can find an equation for x by multiplying both sides by t. So we have x is equal to t multiplied by a cos t plus b sine t plus t. And this is our answer, because we found an equation for the displacement in terms of t. So now that we've answered our question, let's find out where the marks are. You get 1 mark for solving the auxiliary equation, You get another mark for finding the complementary function, so a cos t plus b sin t. You get another mark for finding the general form of the particular integral, so lambda t plus mu. Any constants would be fine over here as long as it's of a linear form. You get another mark for differentiating and solving in order to find lambda and mu. You get another mark for writing down the correct solution of v, so v is equal to a cos t plus b sin t plus t. You get another mark for using this substitution, that v is equal to x over t, and you get your final accuracy mark for arriving at the correct conclusion. So in part C, we want to state what happens to the displacement of C as t becomes large. And thus we want to comment on the model with reference to this long-term behavior. So this is our function x, which shows our displacement in terms of t. Well, if you increase t over here, what's going to happen is that our displacement x is going to become very, very large. Let's examine why. Well, when t becomes very, very large, what changes? So straight away, you're going to have x is equal to t squared, which is a polynomial that grows very large as t becomes large, plus t multiplied by a cos t plus b sin t. Now this is always large and positive, but this requires a bit more thinking. What if a and b are both very negative numbers? Then wouldn't this be less than t squared? Well, a cos t plus b sin t doesn't actually grow in the grand scheme of things, because cos t and sin t are functions that oscillate between -1 and 1, and thus as t becomes very, very large, a cos t can really only grow between -a and a. Similarly, b sin t can really only change between b and -b. Hence, eventually, this t squared will outgrow this t multiplied by a cos t plus b sin t if t becomes very, very large, because this part inside the bracket oscillates between a certain set of values, whereas t squared will always keep growing, and thus the displacement will also always keep growing. So thus, for large t, the displacement gets very large and positive. In part II, we need to comment on the model with reference to this long-term behavior. So our model is of a vibrating spring fixed at one end, and it has an external force acting on it such that the center of the spring moves in a straight line. We are measuring the displacement of the center of the spring from a fixed point O. Well, if this is our spring over here, and our fixed point O is over here, and our center of the spring is over here, if this center moves about at increasingly large distances, this model suggests that it can continue to do this infinitesimally. But realistically, if you do that to a spring, the spring is going to break, because the spring is eventually going to reach its elastic limit. So thus the answer to this question is that the model suggests the midpoint of the spring moving relative to the fixed point has large displacements when t is large, and that's unrealistic, because the spring may reach an elastic limit, causing it to break. Great, so now that we've answered part C, let's find out where the marks are. Well, you get 1 mark per point that you make, because this question is 2 marks and it has a part I and part II, for a total of 2 marks. So in this question, we have a differential equation, the second derivative of y minus 2x multiplied by the first derivative of y plus y is equal to 0. We need to show that the fifth derivative of y is equal to ax multiplied by the fourth derivative of y plus b times the third derivative of y, where a and b are integers to be found. Now, in order to answer this question, we must first notice that in our equation I, we have the second derivative of y as the highest order derivative of y. But in our show that, we have the fifth derivative of y as our highest order derivative of y, which suggests that in order to go from equation I to this equation over here, we need to differentiate it. Because our highest order derivative of our show that is the fifth derivative of y, it gives us a hint that we might need to differentiate our equation 3 times. Now let's differentiate our equation I then. So we have the second derivative of y minus 2x multiplied by the first derivative of y plus y is equal to 0. Now if we differentiate this entire equation, we'll need to differentiate each of these terms individually. So for example, the derivative of the second derivative of y will just be the third derivative of y, and the derivative of plus y will just be dy by dx. Now this will be equal to 0. Now how do we differentiate the terms in the middle? In order to differentiate 2x multiplied by dy by dx, we need to use the product rule, which states that the derivative of ub is equal to u dash v plus v dash u, where u dash and v dash are the derivatives of u and v respectively. So thus, our derivative of minus 2x multiplied by dy by dx will be equal to minus 2x multiplied by the derivative of dy by dx, which will just be the second derivative of y. So the second derivative of y minus 2 multiplied by the derivative of x with respect to x, which will just be 1, multiplied by dy by dx. And thus, our derivative of minus 2x multiplied by dy by dx is equal to minus 2x multiplied by the second derivative of y minus 2 multiplied by the first derivative of y. Now we can see that we have a minus 2 dy by dx over here, and we have a plus dy by dx over here, so we can add them in order to form the third derivative of y minus 2x multiplied by the second derivative of y minus dy by dx is equal to 0. Now this is what we get when we differentiate our initial equation I once, so let's differentiate it 2 more times. So if we differentiate it 1 more time, we get, remembering that we're differentiating each term and using the product rule on the middle term, we get the fourth derivative of y minus the second derivative of y minus 2x multiplied by the third derivative of y minus 2 times the second derivative of y is equal to 0. And we can simplify this once again to give you the fourth derivative of y minus 3 times the second derivative of y minus 2x multiplied by the third derivative of y is equal to 0. Remember, this equation over here is our first derivative of I with respect to x, and this over here is our second derivative of I with respect to x. Remembering that we get our second derivative of I with respect to x by differentiating our first derivative of I with respect to x. Over here we identify that we need a fifth order derivative of y, so thus in order to get our fifth order derivative of y, we need to differentiate our second derivative of I with respect to x 1 more time. So let's once again differentiate this, remembering to differentiate each terms, and in order to differentiate the 2x multiplied by the third derivative of y, remembering to use the product rule. So we have the fifth derivative of y minus 3 times the third derivative of y minus 2x multiplied by the fourth derivative of y minus 2 times the third derivative of y is all equal to 0. Once again, we can simplify this by combining the terms with the third derivative of y together. So we have the fifth derivative of y minus 5 times the third derivative of y minus 2x multiplied by the fourth derivative of y, and this is all equal to 0. Now our question wants our answer in the form of the fifth derivative of y is equal to ax multiplied by the fourth derivative of y plus b multiplied by the third derivative of y. And because our equation over here, our differential equation, is equal to 0, then we can move all of the terms that aren't the fifth derivative of y onto the right hand side to give you the fifth derivative of y is equal to 2x multiplied by the fourth derivative of y plus 5 times the third derivative of y. And thus, if we compare our answer over here to our show that over here, we can see that a is equal to 2 and b is equal to 5. And thus, this is our answer to our show that question. So now that we've answered our question, let's find out where the marks are for part A. So for part A, you get both a method and an accuracy mark for correctly differentiating our initial differential equation I. So we get a method mark and an accuracy mark for correctly differentiating. We get another method mark for differentiating this in order to find the fourth derivative of y. And we get a final accuracy mark for arriving at the correct solution where a is equal to 2 and b is equal to 5. So in part B, we want to hence find a series solution in ascending powers of x as far as the term in x to the power 5 of the differential equation I, where y is equal to 0 and dy by dx is equal to 1 and x is equal to 0. So these over here are our initial conditions. Now, in order to find a series solution of our equation, we can use the Taylor series, which states that at x is equal to c, f of x is equal to the sum of the nth derivative of f at point c all over n factorial multiplied by x minus c all to the power of n to infinity, as represented by this formula over here. Now, we only want the terms up to x to the power of 5. So what we want to do is we want to find up to the fifth derivative, which we have found in part A. Now, if we look at our formula, this formula relies on the fact that we know what f of x is and the derivatives of f of x, and we also want to know what c is. Well, at x is equal to c, we have using our initial conditions that x is actually equal to 0. So instead of this, our formula looks something like this. F of x is equal to f of 0 plus the first derivative of f at 0 multiplied by x, because x minus c will just be x because c is equal to 0, plus the second derivative of f at 0 all over 2 factorial multiplied by x squared, plus in general the nth derivative of f at 0 all over n factorial multiplied by x minus c to the power of n. Well, x minus c will just be 0, so it will be x to the power of n all the way to infinity. Now, we only want the series solution as far as the term x to the power of 5, so at most we want our n to be 5. Now, as you can see using our formula over here, in order to find f of x as a series expansion, we need to know what the derivatives of f of x are. Well, we actually do know what the derivatives of f of x are, because we found it in our part A. We were given that the second derivative of y is equal to 2x multiplied by dy by dx minus y. How do we know this? Well, we can just move all of the terms that aren't our highest order term or our highest order derivative onto the right hand side. We can also use this to find an equation for our third derivative of y, our fourth derivative of y, and our fifth derivative of y in part A. So by rearranging our differential equations, we get these equations over here. Now, once again, our initial conditions are that at y is equal to 0, the derivative of y is equal to 1 and x is equal to 0, and thus we can use this and the formula that we found above for our series expansion in order to find out the series expansion up to x to the power of 5 for our differential equation I, which is this equation over here. Okay, so let's work term by term. F of 0 will just be the value of y when x is equal to 0, and using our initial conditions we know that that's equal to 0. So f of 0 will be 0. F dash of 0, so the first derivative of f when x is equal to 0, will just be dy by dx when x is equal to 0, and that will be 1 using our initial conditions. Now we want to find our second derivative of f when x is equal to 0. Well, we can use our equation over here in order to find that out. We know that our second derivative of y is equal to 2x multiplied by dy by dx minus y. Now we can substitute in our initial conditions that we found in order to find the value of the second derivative when x is equal to 0. So we will have f dash dash of 0 is equal to 2 times x, which will just be 0, multiplied by dy by dx, which is just 1, minus y, which will be minus 0, and that's equal to 0. So our second derivative of f at x is equal to 0 will just be 0. Similarly, we can do the same thing for the next three differential equations. So the third derivative of f will just be, well, dy by dx will be 1, plus 2 multiplied by x, which will just be 0, multiplied by the second derivative of y, well, this is 0, so 2 times 0 will just be 0. The third derivative of f will just be 1. Let's continue this for our remaining two differential equations, remembering each time to substitute in our values from our initial conditions and also the values that we worked out previously. And thus we have our values of the derivatives of f needed in order to write out our series expansion. Now notice that the zero derivative of f, which is over here, f of 0 is equal to 0, is 0. And so is the second derivative of f, and so is the fourth derivative of f. So we know that in our equation over here, or in our expanded series expansion, the terms with f of 0, the second derivative of f, and the fourth derivative of f won't be included in our expansion, because anything multiplied by 0 will just be 0. So thus we should only focus on the first derivative of f, the third derivative of f, and the fifth derivative of f. So let's substitute our differentiated values of f into our equation above. So we have f of x is equal to, well, f of 0 will be 0, so it will be 0 plus the first derivative of f multiplied by x at x is equal to 0, so it will be 1x, which will just be x, plus, well, the second derivative of f at x is equal to 0 will just be 0 over here, so it will be plus 0, plus, now the third derivative of f at x is equal to 0 will be 1, so we have to do 1 over 3 factorial, because at this point n is equal to 3, 1 over 3 factorial multiplied by x to the power of 3, which would be 1 over 6 multiplied by x to the power of 3. Remembering that 3 factorial is equal to 3 times 2 times 1, which would just be equal to 6. Now the fourth derivative of f at x is equal to 0 would be 0 as well, so it will be added another 0, plus, now the fifth derivative of f is not 0, it's 5 at x is equal to 0, so we once again need to use our formula. So we have the fifth derivative of f at x is equal to 0, which is 5, all over, well, n at this point is 5, so it will be 5 factorial multiplied by x to the power of n. Well, n will be 5, so it will be x to the power of 5. And our equation only wants us to find our series expansion up to the fifth term, or x to the power of 5. And hence, this is our solution. We can simplify this a bit because we can get rid of all the zeros and just leave our terms that actually have values. So we have x plus 1 over 6 multiplied by x cubed plus, well, 5 over 5 factorial will be 5 over 5 times 4 times 3 times 2 times 1. And the 5's cancel, so you have 1 over 4 factorial. 4 factorial will be 24. So we will have 1 over 24 multiplied by x to the power of 5. And there are more terms added, but we only want our terms up to x to the power of 5. And once again, we want it in ascending powers of x, and we found it in ascending powers of x. Ascending means that the powers increase as you read from left to right, and hence we have solved our question. This is our series expansion for our differential equation, I, using the initial conditions that we were given earlier. Now that we found the answer to part B, let's find out where the marks are. You get 1 mark for finding the second derivative of f using our initial conditions up here. I'm showing that that's equal to 0. You get another mark for doing the same thing for the third, the fourth, and the fifth derivative. So finding out that the third derivative of f at x is equal to 0 will be 1, the fourth derivative of x at x is equal to 0 is equal to 0, and the fifth derivative of x at x is equal to 0 will be 5. And you get a further accuracy mark for doing these correctly. You get another mark for noting that our equation will be something of this form. And you get a final accuracy mark for plugging it into our formula to give you f of x, which is just x plus 1 over 6 multiplied by x cubed plus 1 over 24 multiplied by x to the power of 5. Remember the plus dot 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 over here, because this series expansion actually goes into infinity, but we've really only included our first 3 terms over here. In this question, we're given that the normal to the parabola y squared is equal to 4ax at the point P, where P has the coordinates ap squared and 2ap, passes through the parabola again at the point Q, where Q has the coordinates aq squared, 2aq. The line OP is perpendicular to the line OQ, where O is the origin. We want to prove that P squared is equal to 2. Now the first thing to do when given a parabola question, or any question involving something that you can sketch, is sketching it. So we know that our parabola has the equation y squared is equal to 4ax. So the general form of a parabola looks something like this. But this is our parabola. Now P is any point on the parabola because ap squared and 2ap is the general form of the coordinates of a parabola. So let's say that P is over here perhaps, so this is P. The normal is a straight line through the point P, which is perpendicular to the parabola at that specific point. So it would look something like this. It passes through the parabola again at the point Q. So this is our point Q, which has the coordinates aq squared and 2aq. And P has the coordinates ap squared and 2ap. We're given that the line OP So let's draw the line OP, remembering that O is the origin, so this is OP, is perpendicular to the line OQ. This right here is the line OQ, so this is perpendicular, where O is the origin. Now my diagram isn't 100% correct over here because this does not look like a right angle. However, we know that our graph looks something like this, where POQ is a right angle because OP is perpendicular to the line OQ. Okay, so how do we approach this question? Well, we know many things about the gradients of this graph because we know that PQ is a normal to our parabola. So we can actually find an equation or a formula for the gradient of the normal over here. So how do we do this? Well, you should know that given a parabola y squared is equal to 4ax, then you can find the derivative of the parabola by noting that 2y multiplied by dy by dx is equal to 4a. Now, if you struggle to remember this fact in the exam, you can always get this by differentiating our y squared is equal to 4ax, because by implicitly differentiating our y squared, we get 2y multiplied by dy by dx is equal to 4a by differentiating our 4ax. Now we can solve for dy by dx because remember, once again, we want the gradient of our normal. So if we solve for dy by dx, we get dy by dx is equal to, well, 4a over 2y will just be 2a all over y. And in this particular scenario, we have a value of y because we know that our normal is at the point P. So y must be equal to 2ap as shown by our point P. So thus, dy by dx, or the gradient of our parabola at the point P, is equal to 2a over our value of y, which is 2ap, and that's just equal to 1 over p. Now, this is the gradient of the tangent of the parabola at the point P. So what we really found is the gradient of this line over here. But we don't want the gradient to that line, we want the normal of the parabola at the point P. Well, in order to find the normal, we just take the negative reciprocal of our gradient of the tangent. And thus, the gradient PQ is equal to minus P, because we take the negative reciprocal of 1 over P. Well, now that we have the gradient of PQ, what can we do next? Well, we can actually also find the gradient of PQ another way. Note that we're given 2 points over here, AP squared to AP and AQ squared and 2AQ. And if you're given 2 points on a straight line, you can find the gradient by using the formula y2 minus y1 over x2 minus x1 is equal to the gradient. Now in this case, our y2 will be 2AP, and our y1 will be 2aq. And similarly, our x2 will be ap squared, and our x1 will be aq squared. So let's find the gradient of our straight line then, or our normal, which is pq. Because there's an a at the top and the bottom, we can cancel a's from the top and bottom respectively. So this is equal to 2p minus 2q all over p squared minus q squared. And if you look carefully, the bottom is actually a difference of 2 squares. So this fraction can be actually rewritten as 2 multiplied by p minus q all over p minus q multiplied by p plus q. And you can cancel the p minus q's to give you 2 over p plus q. So this is also another equation for our gradient pq in terms of q. Now, because we know that the gradient that we calculated above is the same as the gradient we just calculated, we can set them equal to each other. So we know that minus p is equal to 2 over p plus q. And by multiplying both sides by p plus q, we obtain minus p multiplied by p plus q is equal to 2. And thus we can simplify this even further to give you minus p squared minus pq is equal to 2. And hence, by bringing all of the p terms to the right hand side, we get p squared plus pq plus 2 is equal to 0. And this is a quadratic equation. But notice over here that we have a q. And in our prove that statement, we want to show that p squared is equal to 2. There's no q in our prove that. So in some way, we need to eliminate our variable q. Well, this is our diagram over here. We know that OP is perpendicular to OQ. So if we can somehow use that fact in order to find a value of q in terms of p, we can substitute that value of q back into our quadratic equation over here in order to find the value of p, or p squared. So how do we use this fact that OP is perpendicular to OQ? Well, we know that the gradient of OP, so the gradient of OP, will be 2AP over AP squared, and that's just equal to 2 over P. Similarly, the gradient of OQ will be 2AQ all over AQ squared, and that would be equal to 2 over Q. Now, because we know that these two are perpendicular, what we know is that the negative reciprocal of one of these gradients is equal to the gradient of the other one, i.e. 2 over P, so let's say this is one gradient, is equal to the negative reciprocal of 2 over Q, which is minus Q over 2. And hence, 4 is equal to minus QP by multiplying both sides by 2 and P. And using this, we can find an equation for Q by dividing both sides by minus P to give you Q is equal to 4 over minus P. Great, so now that we know an equation for Q in terms of P, we can use this in order to substitute back into our quadratic equation above. So we know that Q is equal to 4 over minus P, and thus P squared plus PQ plus 2 is equal to 0 can actually be rewritten as P squared plus P multiplied by 4 over minus P plus 2 is equal to 0. We can simplify this to form P squared minus 4 plus 2 is equal to 0, and thus P squared is equal to 2. And thus we have shown that P squared is equal to 2. Great, so now that we've answered our question, let's find out where the marks are. You get 1 mark for stating this fact, that you can find the derivative of our parabola by implicitly differentiating both the left-hand side and the right-hand side. You get another mark for finding the gradient of the normal, so we get another mark for finding the gradient of PQ. You get another mark for finding the gradient of PQ in this way, by noticing that PQ actually passes through Q as well. You get another mark for obtaining this quadratic over here in terms of P. You get another mark for finding the gradient of MOP and the gradient of OQ, and using this fact to note that Q is equal to minus 4 over P, so you get 2 marks over here. You get another mark for substituting back into our equation, and you get a method and an accuracy mark for rearranging in order to show that P squared is equal to 2. We're given that a tetrahedron has vertices A, B, C, and D with the following coordinates 1, 2, 1, 0, 1, 0, 2, 1, 3, and 10, 5, 5. For part A, we want to find a Cartesian equation of the plane ABC. Now, the first thing you should be thinking about when answering this question is what exactly is the Cartesian equation of the plane? Well, you can rewrite the Cartesian form as x1x plus y1y plus z1z is equal to k, where k is a constant. This Cartesian form comes from its column form, where r dot x1, y1, and z1 is equal to k, where k is the constant once again. Now, what's important to note is that x1, y1, and z1 is actually the normal vector of the plane. So this is our plane over here, and the vector x1, y1, z1 will be the vector like this, where this direction vector is perpendicular to the plane. So this is actually the normal vector. Well, in order to find the normal vector of our plane and our scalar constant, we're going to need a minimum of 3 points. Well, we know that our plane is the plane ABC, so we can use the points A, B, and C in order to find out the equation, or the Cartesian equation, of the plane. Now let's sketch out our plane. So our plane is going to look something like this, where this is the normal vector, and this is perpendicular to our plane over here, and A is over here, B is over here, let's say, and C is over here. Now, as you can see over here, in order to find the normal vector, we can find the vector AB and the vector AC, and find the vector that's perpendicular to both of these vectors in order to find out the normal vector of the plane, because as you can see over here, if our vector is perpendicular to both AB and AC, then it's also going to be perpendicular to our plane pi. So let's find out the column form of the vectors a, b and ac. We will do the position vector b minus the position vector a, and similarly we will do the position vector c minus the position vector a. And now that we have the vectors a, b and ac, we're going to need to find the vector that's normal to both of these vectors. Well, in order to do that, we can use the vector cross product, because the vector cross product, by definition, allows us to find a vector that's perpendicular to two vectors. Well, we need to find AB cross AC, and in order to find the vector cross product of two three-dimensional vectors, we can put them in a 3x3 matrix and calculate the determinant of that matrix. So we have our vector I, our vector j, and our vector k, and our first vector, so -1, -1, -1, and our second vector, 1, -1, 2. So on the second row we have the vector AB, and on the third row we have the vector AC. And by calculating this determinant, we get -2 minus 1i minus -2 plus 1j plus 1 plus 1k. And this is just equal to -3i plus j plus 2k. And this is our normal vector. Now, if we recall our Cartesian equation of our plane, we have x1, y1, and z1 now, because x1 will be -3, y1 will be 1, and z1 will be 2. Thus, we know that our plane will look something like this. R dot, our normal vector, is -3, 1, 2, is equal to some scalar constant k. Now, in order to find the scalar constant, we can just substitute in a value that lies on our plane. So we can substitute in a, b, or c, but in this case, I'm going to just substitute in my position vector a. So we have 1, 2, 1 dotted with -3, 1, 2 is equal to k. And we can perform the dot product on this to get k is equal to 1, and thus our Cartesian equation of the plane is equal to -3x plus y plus 2z is equal to 1. This is thus our answer. Now that we've answered part A, let's find out where the marks are. You get 1 mark for finding AB cross AC. You get another mark for finding our value of k, so our scalar constant. And you get our final mark for then writing out our Cartesian equation. For part B, we want to find the volume of the tetrahedron ABCD. Well, we know that we have our plane containing the points ABC as such. So this is A, this is B, this is C. These are just arbitrary points on the plane. And in order to form our tetrahedron ABCD, D must lie somewhere over here, so somewhere above or somewhere under, but not on the plane. So our tetrahedron will look something like this. Now, in order to find the volume of a tetrahedron, you need to recall the formula. The volume of the tetrahedron is equal to 1/6 multiplied by the magnitude of A dot B cross C. Now in this case, because we calculated the normal of our plane ABC already in part A, we can actually simplify this formula to give you that the volume of a tetrahedron is 1/6 multiplied by the magnitude of the normal vector of our plane ABC dotted with AD. Now once again, we can use our normal vector n over here because B cross C is actually, in our specific example, AB cross AC. And we know what AB cross AC is because that is our normal vector. Now let's use this formula. So we need to find out the value of AD first. Well, our vector AD can be calculated as such. We know that D has a position vector 10, 5, and 5. And we know that A has a position vector 1, 2, 1. So by subtracting A from D, we can get the vector AD, which is just 9, 3, and 4. Thus, plugging this into our formula we have above, we get a sixth multiplied by the magnitude of -3, 1, 2, which we get from our cross product we calculated in part A, dotted with 9, 3, 4, which is our vector AD, and this will just be equal to 1/6 multiplied by -27 plus 3 plus 8, or the magnitude of this, and this will just be equal to 8/3. And thus this is our volume of our tetrahedron. Now that we've answered part B, let's find out where the marks are. You get 1 mark for stating the volume of a tetrahedron formula using our normal. You get another mark for actually using our formula, and you get your final accuracy mark for arriving at 8/3 units. So in part D, we need to show that the volume of our tetrahedron ABCD is 45 times the volume of the tetrahedron ABEF. For part C, we're given that the plane pi has the equation 2x minus 3 plus 3 is equal to 0. We're also given that the point E lies on the line AC and the point F lies on the line AD. Given that pi contains the point B, the point E, and the point F, we need to find the value of K such that AE is equal to KAC. Well, in part C, we're only asked to look at AE and AC. So let's actually draw our line AC first. So this is our line AC, and we know that point E lies somewhere on here. So point E can lie here. However, bear in mind that E could also lie over here, or just somewhere on the line AC. But we're going to assume that it lies somewhere in the middle for now. So our question C actually tells us that our vector equation AE, which is this direction vector, is a multiple of AC, but it's of a specific scalar constant K. Well, we know this from our diagram because E will lie on AC. Now we can actually calculate the value of our position vector E because we know that our direction vector AE is a scalar multiple of our direction vector AC. Therefore, we can actually rewrite our direction vector AE as KAC. Thus, in order to get to our position vector E, we need to use a position vector of A and add our direction vector KAC to A in order to get to our position vector E. So thus, our position vector E can be rewritten as A plus KAC. And because we actually know what A is, and we can write AC in terms of K, we can write this in column form. So our position vector E can actually be rewritten as, well, we know what A is 1, 2, 1. So we will have 1, 2, 1 plus K multiplied by AC. Well, AC will just be 1 minus 1 and 2, as this will just be equal to 1 plus K, 2 minus K, and 1 plus 2K. Now, because this point actually lies on our plane pi, as given by this line over here, our plane pi contains the point B, the point E, and the point F, and this is our point E, we can substitute our point E into our equation for our plane in order to find out the value of K. So we will have 2 multiplied by our x-coordinate for our position vector, so it's 1 plus K, minus 3 multiplied by our y-coordinate of our position vector, so 2 minus K, plus 3 is equal to 0. And using this, we can solve the equation for K, so we will have 2 plus 2K minus 6 plus 3K plus 3 is equal to 0. And hence, K is equal to 1/5. And this is our answer to the question, because we want to find the value of K such that AE is equal to KAC. Now the marks for C are allocated as such. We know that AE is equal to KAC, and therefore we get a mark for writing our position vector E as such, 1 plus K, 2 minus K, and 1 plus 2K. You get another mark for noticing that E lies on our plane, so we can substitute this value of E into our plane equation, and you get a final mark for getting the accuracy correct, that K is equal to 1/5. Now let's first draw our tetrahedron ABEF, which will look something like this. Now regularly, using our volume of our tetrahedron formula, we'd find this by doing 1/6 multiplied by the magnitude of AB cross AE dotted with AF. This is AB, this is AE, and this is AF. However, we're given that AF is equal to 1/9 times by AD, and thus this can be rewritten as 1/6 multiplied by the cross product of AB and AE dotted with 1/9 AD. We also found out the value of AE in terms of AC from our previous part. We know that our AE will be equal to 1/5 AC, and thus we can actually rewrite this once again to give you 1 over 6 multiplied by the magnitude of AB cross 1 over 5 AC dotted with 1 over 9 AD. Now, because 1 over 5 and 1 over 9 are just scalars, we're able to take them out of our cross product and our scalar product in order to give you 1 over 6 multiplied by AB cross AC dotted with AD, and this is multiplied by 1 over 45 because 1 over 5 multiplied by 1 over 9 is 1 over 45. And if you notice from the calculation that we did from part B, this is our formula for the volume of our tetrahedron. And because this over here is our volume of our tetrahedron ABEF, this means that our volume of ABCD is 45 times the volume of ABEF, as this is the volume of ABCD. Hence, we've answered our question. The volume of ABEF is 45 times smaller than our volume of ABCD. Now that we've answered part D, let's find out where the marks are. You get 1 mark for noticing that you can substitute in our AE and our AF as such. And you get another final accuracy mark for taking out the 1 out of 45 from the 1 over 5 and the 1 over 9. In this question, P and Q are 2 distinct points on an ellipse described by the equation x squared plus 4y squared is equal to 4. We're given that the line L passes through the point P and the point Q. We also know that the tangent to the ellipse at P and the tangent to the ellipse at Q intersect at the point RS. Thus, we need to show that an equation for the line L is 4sy plus rx is equal to 4. Now over here we have the equation of our ellipse. X squared plus 4y squared is equal to 4. Now, because of dealing with tangents of the ellipse, a good first step to take would be to find the gradient of our tangents at those specific points. And the way we do that is by implicitly differentiating our ellipse equation, x squared plus 4y squared is equal to 4, to get an equation for dy by dx. So if we implicitly differentiate x squared plus 4y squared is equal to 4, we get 2x plus we multiply our 4 by our 2 in order to get 8y multiplied by dy by dx is equal to 0, and we can thus rearrange this to get dy by dx. So dy by dx will be equal to minus 2x over 8y, which can be simplified to minus x over 4y. Well, now that we have the gradient of the ellipse at any point, let's find the gradient of the ellipse at points P and points Q. Well, we don't actually have a coordinate for P at the moment, so let's just put in a general point that P can be described as the coordinates xp and yp. And thus, using P's general coordinates, we can plug in our values of x and y at point P in order to get the gradient of our tangent at point P. So thus, dy by dx at point P, so when x is equal to xp, is equal to minus xp all over 4yp. Well, if this is our gradient at point P, then we can find the equation of the tangent at point P by substituting this gradient and our coordinates xp, yp into our formula for a straight line. So we will get y minus yp is equal to minus xp over 4yp multiplied by x minus xp. By multiplying our left-hand side by 4yp, we can simplify this a bit more to form 4yp multiplied by y minus 4yp all squared is equal to minus xpx plus xp all squared. Now notice that we have a yp all squared over here and an xp all squared over here, and we have a ypy over here and an xpx over here. Now, because these terms look similar to one another, I'm going to move the squared terms all on one side and the non-squared terms all on one side too. So we will have 4ypy plus xxp is equal to 4yp squared plus xp squared. Now look on the right hand side. 4yp squared plus xp squared is oddly similar to the equation of our ellipse, x squared plus 4y squared is equal to 4. In fact, it's exactly the same, except that we've substituted in our coordinates xp and yp into our equation of the ellipse. Well, because we know that at any point on the ellipse, x squared plus 4y squared is equal to 4, and we know that our point P is on our ellipse, we also know that 4yp squared plus xp squared is equal to 4, because our equation is satisfied at this point. Thus, we can actually set the right-hand side as equal to 4. So 4yp y plus xp is equal to 4. Because we have an equation for p over here, if we let q's general coordinates be xq, yq, we can actually obtain a similar equation for q as we did for p, because we would just need to change the yp and the xp for xq and yq and use our same working again. So we have 4yqy plus xxq is equal to 4. Now, because these equations are equal to 4, we can set them equal to one another. So we have 4ypy plus xxp, well, that's equal to 4, but so is 4yqy plus xxq. So this is equal to 4yqy plus xxq. Now, let's recall this information over here. We have the tangent to the ellipse at P and the tangent to the ellipse at Q intersect at the point RS. Well, these two equations are the equations to our tangents at the point P and the point Q. So thus we know that these equations must be satisfied at the point RS. And similarly, 4ypy plus xxp is equal to 4yqy plus xxq must also be satisfied at the point RS, because these two equations are satisfied at the point RS. So let's substitute in RS into our equation over here. So we have 4yp multiplied by s plus r multiplied by xp is equal to 4yq multiplied by s plus r multiplied by xq. Now let's observe what we have over here. We have a yp and an xp, and a yq and an xq. And we need to show that the equation of the line L is 4sy plus rq is equal to 4. Well, what do we need in order to calculate an equation for a line? Well, an equation, or the general equation for a line, can be written as y is equal to mx plus c. And we can find this by doing y minus y1 is equal to m multiplied by x minus x1. Now from this equation, we need to somehow obtain our values of y1, m, and x1. Well, it should be easy to find y1 and x1 because y1 and x1 can be either the points P or the points Q. So y1 could be yp, x1 could be xp, or y1 could be yq, and x1 could be xq. So we don't actually need y1 and x1. However, we do need m. And how can m be written? Well, because the line L passes through the points P and the points Q, then m can actually be rewritten as yp minus yq all over xp minus xq. Now let's look at our equation over here again. We have a yp and an xp and a yq and an xq. So let's somehow try to rewrite our equation in this form over here in order to get the gradient of our line. So let's move yp and yq onto the same side. And similarly, let's move xp and xq on the same side. So we have 4s multiplied by yp minus yq is equal to r multiplied by xq minus xp. And by rearranging in order to get something of this form, we get yp minus yq all over xq minus xp is equal to r over 4s. Now, this is so close to what we have over here, but it's not quite the same because we have an xq minus xp on the bottom and not an xp minus xq. So let's multiply both sides by minus 1 in order to get xp minus xq. So we will have yp minus yq all over xp minus xq is equal to minus r over 4s. And this is our gradient for our line, PQ. Great, now let's just substitute this into our formula that we have over here using the coordinates xp, yp, but you could also use the coordinates xq, yq. So y minus yp is equal to m, which is minus r over 4s, multiplied by x minus xp. Let's multiply both sides by 4s and multiply out this right hand side bracket to give you 4sy minus 4syp is equal to minus rx plus rxp. And now let's move the terms with p's onto the right hand side and the terms without p's on the left hand side. So we have 4sy plus rx is equal to 4syp plus rxp. Now look at the right hand side, and let's go back up to earlier in our question. We have over here that 4yp multiplied by y plus xxp is equal to 4. So really, we can actually rewrite the right hand side as 4, because 4syp plus rxp is equal to 4. So 4sy plus rx is equal to 4. And this is what our question wanted us to prove. So hence we've shown our question. So now that we've answered our question, let's find out where the marks are. You get 1 mark for finding dy by dx is equal to minus x over 4y. You get another mark for finding the equation of the tangent at xp and yp. So this over here. You get another mark for solving this question and obtaining this over here and using the fact that 4yp squared plus xp squared is equal to 4. So there's another mark. You get another mark for noticing that because they intersect, you can substitute in the values of rs. So you get a mark over there. And you get 2 marks for finding the gradient, 1 for attempting to find the gradient, and another mark for actually finding the gradient. So you get 1 mark over here and another mark over here. You get another mark for finding the equation of the line L, so in this form, and you get your final mark for arriving at the correct conclusion. In this question, we have a graph shown in figure 1 that has the equation h of x is equal to 45 plus 15 sine x plus 21 sine x over 2 plus 25 cos x over 2, where x is between 0 and 40. For part A of this question, we need to show that the derivative of h, so dh by dx, is equal to t squared minus 6t minus 17 multiplied by 9t squared plus 4t minus 3 all over 2 times 1 plus t squared all squared, where t is equal to tan of x over 4. Well, seeing that in part A we want to find the derivative of h of x, let's first differentiate h of x in order to get dh by dx. Well, the derivative of 45 will be 0, so dh by dx will be equal to 0 plus the derivative of 15 sine x, which is 15 cos x, plus the derivative of 21 sine x over 2, which is 21 over 2 cos x over 2, plus the derivative of 25 cos x over 2, which is minus 25 over 2 sine x over 2. Great, so now that we have dh by dx, we should use our substitution that t is equal to tan x over 4 in order to find the equation of dh by dx in terms of t. Well, how do we do that? We don't have anything in terms of tan x over 4 in our equation. Well, you can see over here that although we don't have any tan x over 4s over here, in our arguments of our trigonometric functions, we have x over 2. And if you recall the use of t-Formulae, we can use t-Formulae in order to substitute tan of x over 4 into our equation, as if t is equal to tan x over 4, then sine of x over 2 is equal to 2t over 1 plus t squared, cos of x over 2 is equal to 1 minus t squared over 1 plus t squared, and tan of x over 2 is equal to 2t all over 1 minus t squared. You must memorize these t-Formulae for the exam. So straight away we can substitute our sine of x over 2 and our cos of x over 2 into our equation. So dh by dx is equal to 15 cos x plus 21 over 2 multiplied by cos x over 2, which is 1 minus t squared all over 1 plus t squared, minus 25 over 2 sine of x over 2. Well, sine of x over 2 will be 2t over 1 plus t squared, so it will be minus 25 over 2 multiplied by 2t all over 1 plus t squared. Now, this still isn't quite done yet, because we have a cos x over here, but we only want our equation in terms of t. Thus, we need to somehow find a way to write cos x in terms of t. Well, we know over here that tan of x over 2 is equal to 2t all over 1 minus t squared. And if you recall the trigonometric formula again, if we let m equal to tan of x over 2, then cos of x will just be equal to 1 minus m squared all over 1 plus m squared. You can observe that this is very similar to what we have over here, that cos of x over 2 is equal to 1 minus t squared all over 1 plus t squared, except that in this case, m is equal to tan x over 2 instead of tan x over 4. If cos x is equal to 1 minus m squared all over 1 plus m squared, and if m is equal to tan of x over 2, then m is also equal to 2t all over 1 minus t squared. So we can actually expand this out further to give you cos of x is equal to 1 minus 2t all over 1 minus t squared, and this is all over 1 plus 2t over 1 minus t squared for both the top and the bottom bracket. So let's work with this for a second. We have cos of x is equal to 1 minus 2t all over 1 minus t squared all squared all over 1 plus 2t over 1 minus t squared all squared. We can multiply both the numerator and the denominator by 1 minus t squared all squared to give you 1 minus t squared all squared minus 2t all squared all over 1 minus t squared all squared plus 2t all squared. You can expand this out to give you t to the power 4 minus 2t squared plus 1 minus 4t squared all over t to the power 4 minus 2t squared plus 1 plus 4t squared. And you can simplify this once more to give you t to the power 4 minus 6t squared plus 1 all over t to the power 4 plus 2t squared plus 1. So now that we have cos of x is equal to t to the power 4 minus 6t squared plus 1 all over t to the power 4 plus 2t squared plus 1, we can then find out our value of dh by dx in terms of t. So dh by dx is going to be equal to, well, we want 15 cos of x, which is 15 multiplied by this over here, so it's 15 multiplied by t to the power 4 minus 6t squared plus 1 all over, well, the bottom can actually be rewritten as t squared plus 1 all squared. So this is 1 plus t squared all squared plus 21 over 2 multiplied by 1 minus t squared over 1 plus t squared. So plus 21 over 2 multiplied by 1 minus t squared over 1 plus t squared minus 25 over 2 multiplied by 2t all over 1 plus t squared. And now in order to get our result that we want, we need to put this all into one fraction. So dh by dx is going to be equal to, well, in order to simplify this, let's try to get all of our fractions to have the same common denominator. So we can see over here that our first fraction has a factor of 1 plus t squared in our denominator, and so do all of the others. So let's try multiplying both our numerator and our denominator of our last two fractions by 1 plus t squared, and try multiplying our numerator and denominator of our first fraction by 2. Give you 30 multiplied by t to the power 4 minus 6t squared plus 1 all over 2 multiplied by 1 plus t squared all squared. You can see that this over here is exactly the same as this over here. I've just multiplied both the numerator and the denominator by 2 plus 21 multiplied by 1 minus t squared multiplied by 1 plus t squared all over 2 multiplied by 1 plus t squared all squared minus 25 multiplied by 2t multiplied by 1 plus t squared all over 2 multiplied by 1 plus t squared all squared. Now that they have the same denominator, let's group up all of our fractions together. So we have dh by dx is going to be equal to 30 t to the power 4 minus, well, 30 times minus 6 will be minus 180, so minus 180 t squared plus 30 plus 21 multiplied by, this is a difference of two squares, so this will be 1 minus t to the power 4 minus, well, 25 multiplied by 2 will be 50, so it will be 50t multiplied by 1 plus t squared, and this is all divided by 2 multiplied by 1 plus t squared all squared. And thus this will be equal to 30t to the power 4 minus 180t squared plus 30 plus 21 minus 21t to the power 4 minus 50t minus 50t to the power 3 all over 2 multiplied by 1 plus t squared all squared. And you can actually group up all of the terms over here to give you 9t to the power 4 minus 50t cubed minus 180t squared minus 50t plus 51 all over 2 multiplied by 1 plus t squared all squared. And this can be factorized to give you t squared minus 6t minus 17 multiplied by 9t squared plus 4t minus 3. And this is all over 2 multiplied by 1 plus t squared all squared. And this is actually the same as our show that question over here, and thus we have actually shown our answer. Great, so now that we've answered our question, let's find out where the marks are. You get 1 mark for differentiating our h of x. You get another mark for substituting in our 1 minus t squared all over 1 plus t squared, and our 2t all over 1 plus t squared for our dh by dx. You get another mark for actually working out cos of x and substituting our substitution into our dh by dx. You also get an accuracy mark for doing this correctly. You get another mark for actually putting them all under the same common denominator. And you get your final accuracy mark for arriving at the correct conclusion. So if we look at our question after this, we're now given a new graph, but as you can see, it's actually very similar to the graph of h of x that we had before, so let's keep that in mind. So our new graph in figure 2 shows a graph of predicted tide heights in meters for Portland Harbour from 8 o'clock on the 3rd of January 2017 to the end of the 4th of January 2017. The graph of kh of x, where k is a constant and x is the number of hours after 8 o'clock on the 3rd of January, can be used to model the predicted tide heights in meters for this period of time. For part B, we need to suggest a value of k that could be used for the graph of kh of x to form a suitable model. And for part II, we need to ask why may such a model be suitable to predict the times when the tide heights are at their peaks, but not to predict the heights of these peaks. So let's first answer part I. So for part I, we need to suggest a value of k that could be used for the graph of kh of x in order to form a suitable model. Well, let's look back at our graph h of x. So this over here is our graph of h of x. And let's examine our graph in figure 2. As I mentioned before, they're both very, very similar in shape, but they're not quite the same, because h of x has a maximum amplitude of about 91, and our graph in figure 2 has a maximum amplitude of about 1.75-ish. So somehow we need to use a graph transformation in order to transform this graph into this graph over here. Well, we don't need to change anything in the x-axis because the time periods remain approximately the same. So the only thing we need to change is our amplitude of our graph. Well, how do we do that? Well, if you recall, if you multiply any graph h of x by some sort of constant k, where k is less than 1 and greater than 0, what's going to happen is that you're effectively going to be squashing the amplitude of the graph. So right now, h of x looks something like this, but we want it to actually look something like this. So as you can see, the turning points are the same, but we just have a different amplitude. This graph over here is what we're trying to find over here, and in order to do that, we need to make an estimate of what the scalar factor could possibly be. So in order to answer this question, let's actually examine the intersection of the y-axis of both of our graphs. So in figure 2, our y-axis is intercepted over here, and this is about 1.55. Our graph of h of x intersects our axis at 70, and thus, in order to scale down our graph of h of x down to our graph in figure 2, we need to multiply it by a factor of 1.55 all over 70, which is equal to 31 over 1400. You can look closely that the question asks us to suggest a value of k, so your value of k might be slightly different, but the mark scheme wants our answer within a range, and this actually works within our range. For part II, we want to ask ourselves, why may such a model be suitable to predict the times when the tides are at their peaks, but not to predict the heights of these peaks? Well, if you look at our two graphs, our graphs both oscillate in this fashion, where there's initial peak, and then a small peak, and then initial peak, and then a small peak, and etc. This idea of oscillating with an initial peak and then a smaller peak is called bimodal oscillation. And if you look at the axes of our graphs, both of our graphs oscillate bimodally with about the same periodicity. However, this question is 3 marks, so we would have got 1 mark over here and another mark over here, so it suggests that we need to find another mark in order to answer this question fully. So why can't we use this model to predict the times when the heights are at their peaks, but not to predict the actual heights of these peaks? Because surely after we've transformed it, we should be able to predict the peaks. Well, if you actually look at our graph over here, and if we draw a straight line from our first peak to our last peak, the peaks of our oscillation actually change. We can't actually infer the amplitude of our peaks from our transformed graph. But if we compare that to h of x has fixed peaks for its large and small peaks. So thus we can't really infer the heights of the tide at their peaks using our transformed h of x. So it's not suitable for predicting the heights since the heights of the peaks vary over time, but the graph of h of x has a fixed peak height. So for part B, you get 1 mark if your value of k is within the range 1 over 40 and 1 over 60, which this is, and you get 1 mark each for each of these points that you make. So for part C, we want to use figure 2 and the result of part A to estimate to the nearest minute the time of the highest tide height on the 4th of January 2017. So the highest tide height suggests that we need to find the turning point of our graph. Because at our turning point, we've got the derivative is equal to 0 because there's a tangent. But if you look at our graph, there are actually 4 tangents. So there is a tangent over here, a tangent over here, a tangent over here, and a tangent over here before it starts to repeat, or it starts to oscillate. Now, we can show this because in our equation over here, dh by dx, if we set dh by dx is equal to 0, we have 0 is equal to t squared minus 6t minus 17 multiplied by 9t squared plus 40 minus 3 all over 2 multiplied by 1 plus t squared all squared. If we multiply both sides by 2 multiplied by 1 plus t squared all squared, we get 0 is equal to t squared minus 6t minus 17 and 9t squared plus 40 minus 3. Now, because these are the solutions in which our graph will have a tangent, we're going to have 4 distinct solutions over here. So you can solve these using whatever you use in order to solve quadratic equations. In this case, I'm going to use the quadratic formula to give you the answers of t is equal to 3 plus or minus root 26 via this fraction over here, and t is equal to minus 2 plus or minus root 31 all over 9 using this fraction over here. Now, if you recall, t is equal to tan of x over 4, and we need to find our value of x. But you also have to remember that we need to find the smallest positive value of x to give us our first peak over here, because if we find our other positive values of x, we're going to end up with these turning points over here, which does not correspond to our highest peak. Well, how do we do this from these 2 equations? Well, first of all, let's find out x from each of these equations. So we have, from our first 2 equations, x is equal to 4 multiplied by arctan of t. And thus, using these equations over here, for our principal values of x, we're going to get x is equal to 5.79, which is what you get when you substitute t is equal to 3 plus root 26, minus 4.50, which is what you're going to get if you substitute t is equal to 3 minus root 26, 1.5095, which is what you're going to get when t is equal to minus 2 plus root 31 all over 9, and minus 2.79, which is what you're going to get when t is equal to minus 2 minus root 31 over 9. Now we only want the positive values of x, so we need to change these into their positive forms. And because our graph oscillates periodically, we need to add 4 pi. But why do we have to add 4 pi and not just pi? Because don't you find the other values of tan by adding pi only? Well, over here this is not the case because our argument is x over 4. So in order to find the other principal values of our tan function, we need to actually add 4 pi instead of just pi, because then we'll have 4 pi over 4, which is equal to pi, which is what we get in our argument. So if we add 4 pi to each of our values, we get x is equal to 5.79, and minus 4.50 plus 4 pi will be equal to 8.067. 1.5095 is positive, so we can leave that there. And minus 2.79 plus 4 pi will be equal to 9.776. Now we can see over here which values of x correspond to which peaks because they go in ascending order, but we want our smallest positive value of x to correspond to this first peak over here. So our smallest positive value of x will be 1.5095. So 1.5095. Okay, so if 1.5095 is our smallest positive value of x, it means that we need to use this in order to answer our question. Well, we can't substitute in 1.5095 straight away because our question actually wants us to find the highest tide height on the 4th of January 2017. And in order to do that, we need to find this height over here. And 4th of January actually starts over here. And between these two peaks, this peak is bigger than this one. So thus we need to find this third peak over here. So if this can be mapped onto x is equal to 1.509, then we need to add 4 pi, and we need to add another 4 pi in order to get our value over here, giving you 1.5095 plus 8 pi for the third peak, and that is equal to 26.642, which is the required time. Now, if we actually look back to our graphs, our x-axis over here actually corresponds to the hours. So thus, our x value of 26.642 will actually correspond to 26 hours and 36 minutes. I will do 642 multiplied by 60 is about 36, and 26 just represents hours. And this is after 8 AM on the 3rd of January. And thus, if we add 26 hours and 36 minutes after 8 AM on the 3rd of January, we get approximately 10:39 AM on the 4th of Jan. So this represents our highest peak. Oh, and I realized that this should be 39 minutes, not 36 minutes. So 26 hours and 39 minutes after 8 AM on the 3rd of January, which is 10:39 AM on the 4th of January. So now that we've answered part C, let's find out where the marks are. You get 1 mark for solving each of the quadratics, so one over here or one over here. Make sure to show your working of how you solved your quadratic, for example by completing the square or using the quadratic formula, in order to get to the full method mark. Now, because this solution is actually the only solution that we need, you don't actually get any marks for solving this solution over here, but only for solving this solution over here. So by finding the corresponding x values for this factor, you get another mark. You get an accuracy mark for actually finding the correct decimal place. You get another mark for recognizing that our maximum occurs at our smallest positive value of x, but we actually need our third peak, so you have to add 8 pi. You get another mark for writing out how many hours this corresponds to, so 26 hours 39 minutes after 8 a.m. And you get your final mark for finding the correct answer, as in the correct time.